Hello everyone, Mr. Fawcett here, and we are back with another AP Calculus lesson. Today we're going to continue our discussion of finding the area between two curves, but now we're going to look at functions in terms of y rather than functions in terms of x. So it's going to change a little bit about how we set up the integral, but the idea is still the same, as far as the top function, the bottom function, finding the limits of integration, etc. To get us warmed up, let's do a little review problem from yesterday. It says find the area between the curves given by f of x and g of x. Those functions are written down for you up there. You're not going to use a calculator to graph the functions, but I will let you use a calculator to evaluate the definite integral once it's written. So we're not going to make you do all the algebra by hand as far as substituting and simplifying, etc. So set it up by hand, and then you can evaluate using a calculator. Pause the video and give it a shot. Okay, so even if you have no idea what these functions look like, you don't really have to, right? We should know that one's a parabola, right? The one that has an x squared, and the other one is a linear function, right? Where it just has an x to the power of 1. But if we don't know exactly where they are on the graph, we can still figure out what our limits of integration are, which one's top and bottom, etc. The first thing we want to do is we want to figure out where the functions intersect, because that's going to give us our limits of integration. So I just need to set f of x equal to g of x. So I'm going to get negative 1/2 x squared minus 2x plus 4 is equal to 1/2 x plus 4. I'm going to get all of the terms on the left-hand side. So I'm going to subtract 1/2 x and 4 from both sides. I get negative 1/2 x squared minus 5/2 x plus 0 is equal to 0. Well, I can factor out a negative 1/2 x. Inside my brackets or parentheses, I'll be left with just an x plus 5. That's going to be equal to 0. So my two solutions are x is equal to 0, x is equal to negative 5. So there's our limits of integration. We're going from negative 5 to 0. Now, we know that I'm going to be doing top minus bottom dx. I just need to figure out whether it's f of x minus g of x or g of x minus f of x. Well, how can I figure out which one has a higher y value along that interval? Well, I'm just going to choose an x value in that interval, substitute it in, and see which function gives me the larger y value. Let's choose negative 1. So, and I'm not going to write all this out, but f of negative 1 would end up giving me 13/2 or 6.5. And again, you can do that in a calculator, that's fine, or you can do it by hand. G of negative 1 would end up giving me 7/2. So that now tells us that f of x is our top function, g of x is our bottom, I'm going to make this equal to our area. So area is equal to the integral from negative 5 to 0 of f of x. So negative 1/2 x squared minus 2x plus 4 minus g of x. And just make sure you put g of x in parentheses, 1/2 x plus 4, close your brackets, dx. And you're ready to jump to a calculator. Pause the video, make sure you punch everything in correctly. They would probably not give you one like this to do by hand on the AP exam anyway, just because it would be tedious algebraically. It's possible, but unlikely. So we are going to go ahead and round to 3 decimal places or truncate. But again, get that practice, substitute into the calculator, make sure you punch everything in right. We should end up getting approximately 10.416. That is the area between these two graphs. And if you wanted to see what they look like, right, you could graph these. You may not have the option on the AP exam, but if you want to look at, what they look like now, you could sketch a little graph. You could graph them. We know that our linear function looks something like this. And our parabola would be shifted. Well, it's going to be an upside down parabola, right? So opening downwards. And it would look something like this. So we just found this area right here. But again, not necessary to know what that picture looks like to figure out that shaded area. Okay, so that was a little review. Let's go ahead and jump to something new. All right, so sometimes you're going to be given functions in terms of y or curves in terms of y. They won't always be functions. And you're going to be asked to find the area between them. Or maybe the area between a function or a curve and the y-axis. We're going to see how these problems are similar to the ones we've been doing and also how they differ. So the first one, before I just kind of tell you how we set them up and how we go about it, I want you to take a look at that area that's shaded on the graph. And you can also look at the integral right here. Does that integral make sense if we're trying to find the shaded region? Maybe we need to switch something about it. Well, what do you think you'd switch? Or maybe you'd leave it the same. Just take a minute to compare the two. Think about what's different about this problem and how that may or may not change our integral. Okay, so maybe right off the bat we notice that something's different here, right? It looks like we're supposed to be integrating with respect to x, but our function's in terms of y, right? We would like those to match, right? If we're going to integrate with respect to x, our function should be in terms of x. Maybe you also notice something about these limits of integration, 0 to 5. Well, it certainly looks like it starts at 0, but does it quite go to 5, this blue area? It looks like it's a little past 5. Also, the shaded region doesn't even come down all the way to the x-axis, right? So if I was trying to find the area under this curve, well, that area would be all the way down to the x-axis. It also wouldn't just stop arbitrarily up here, right? It would continue until we touch the function. So right away we see that, maybe writing this integral in terms of x may not necessarily work, right? Because even if I can figure out, where this intersection point is on our graph, right, and I figure out that interval, well, I'd still have to figure out, well, what's going on with this non-shaded area, right? If that's not shaded, I got to figure out a way to take that out of my integral. I'd also have to figure out a way to take this area out of my integral. So it actually looks like it'd be pretty confusing to write this the normal way in terms of x's. Fortunately, we have another possibility. We could write this in terms of y. Okay, so what I did here, I actually rotated this graph a little bit. Just so that we set it up or we see it visually how we've been seeing these before. I actually rotated it 90 degrees. You can think about rotating it 90 degrees. Whoops. Rotating it 90 degrees in the counterclockwise direction. And then I actually reflected it. So once I rotate it 90 degrees, it looks like this, where this is the positive x side. Sorry, this is the positive y side. Okay, that's if I rotated 90 degrees. And then I actually reflected. So I just reflected it about the x-axis. Then I get a graph that looks like this one over here. And you may find that you don't need to rearrange your graph and look at it how you're used to looking at it in terms of finding area underneath the curve. I'm just going to show you both so that you can see both side by side, and then you can kind of make a decision about what works best for you visually. Some students feel like they need to always see the graph and see the area under the curve vertically. Some are capable of looking at it horizontally. So it'll be up to you, but I'll show you both at first. There's something else we need to look at. So they said, what is the area bounded by the curve, the y-axis, and the line y equals e and y equals e cubed? Well, the line y equals e, this line right here, the line y equals e cubed, this line right here. Over on our other graph, the line y equals e, just after 5, I'll just redo that real quick. And e cubed just after 20. Not that much better, actually. Let's just move it manually. There we go. Just after 20. So on either graph, I'm just going to label these again so they make sense. On either graph, we're looking for the area sectioned off by those restraints. Now we're going to set our integral up the same way we've been doing, except our limits of integration are going to be in terms of y. Okay, so they're not going to be x values. We also are going to be integrating with respect to y because our curve or our function is in terms of y. So let's first start off by looking at it this way, the one on the right. Well, I'm going to take the integral. So the area is equal to the integral from e to e cubed. My function is 15 over y, right? It's in terms of y. And I'm going to be differentiating with respect to y. It's going to come out to be the same thing if I look at this graph over here, right? Then I can look at it, how it was given to me. I'm going from y equals e, that's the lower bound of integration, to y equals e cubed, using the same function. It's in terms of y, so I'm going to be differentiating with respect to y. So this is what would give us the area. You'll notice that it's quite different from this integral right here. Different limits of integration, and we're going to be integrating with respect to y. But the idea still holds, right? The idea that we're finding the function, in this case it's x equals 15 divided by y, and we're integrating that over a specific interval, that's going to give us the area beneath that curve, or between the curve and the x-axis. Now, we can go ahead and integrate this by hand. We could integrate it with the calculator. It doesn't matter. Note that if you did it on the calculator, the process would be exactly the same. You could treat your y's as x's when you're using the calculator, and it's still going to give you the right value, right? You could put in t's, and it would still give you the right value. You just have to make sure that on the calculator, this matches what you're integrating with respect to. Let's go ahead and do it by hand, though. So pause video, see if you can evaluate it by hand. Should not have to use the calculator. You'll see that things simplify out nicely here. So I'm going to get area is equal to, well, the antiderivative of 15 over y is 15 times the natural log of the absolute value of y. I don't need a plus c because it's a definite integral. And then I need to evaluate it from e to e cubed. Well, this gives me 15 times the natural log of e cubed. I don't need the absolute values anymore because e cubed is positive. Minus 15 times the natural log of e. This gives me 15 times 3 minus 15 times 1, which gives me 30. So the exact area between that curve, the y-axis, and the two vertical lines, it depends which graph you're looking at, but the two lines, y equals e and y equals e cubed, is exactly 30. So hopefully you can see the similarities between our process here and what we did yesterday, right? When our functions were in terms of x, we were finding the area between a curve and the x-axis rather than a curve and the y-axis. So you hopefully see the similarities, but hopefully you see the differences that occur here, namely that the limits of integration are in terms of y values rather than x values, and we're going to be integrating with respect to y. Maybe, I don't know how helpful showing you this extra diagram was, or just showing you, how we could make it look kind of like a problem from yesterday. We can just kind of switch the axes around. It's not important how you are able to visualize it, right? What is important is going to be, are you able to determine when you need to set your limits of integration up in terms of y versus when you need to set them up in terms of x? That's what we're going to be focusing on. So let's fill in these blanks, and then we'll do one or two more practice problems. This is kind of just summing up what we talked about earlier. When we are evaluating a definite integral, our limits of integration need to match the variable we are integrating with respect to. So if our function is in terms of y, we're going to need to integrate with respect to y, and vice versa. When we are finding area between a curve and the y-axis, our limits of integration will be boundaries that are in relation to the y-axis. Our function will be in terms of y, and we will be integrating with respect to y. Everything else, though, the other ideas will stay the same. We already did the problem above. We kind of did this in reverse order, so we do not need to finish this one. Let's go ahead and look at page number 4. So we're going to skip this page, and we're going to look at this example right here. So the first thing I want you to think about is, does it make sense to set up an integral for the area between these two functions? Does it make sense to set this integral up in terms of x's or in terms of y's? And I'm specifically thinking about the limits of integration. When we're finding the boundaries, does it make sense to use x values or y values? I understand that they already tell you that the curves are in terms of y's, right? So they're writing this as a function of y. And that can be a giveaway, right? That you should probably think about using limits of integration in terms of y. But let's also think about y, no pun intended, based on what the diagram looks like. And again, maybe you want to rotate it different ways so that you can think about, okay, does it make sense to look at it in terms of x's, horizontally, or y's vertically, etc. Okay, so if I think about looking at it in terms of x's, I would need to go from this x value to this x value. And you'll notice that those two x values are not where the functions intersect, which is usually what we do, right? We'd find where the functions intersect. Those would be our limits of integration. We'd figure out top versus bottom, etc. Here, though, the left endpoint would be the leftmost x value of the orange curve, right? Or if you thought about it in terms of y, it would be the minimum x value, right? For the blue curve, it's actually going to be the maximum x value. So we would actually have to go through a different sort of process here. We'd have to find a minimum and a maximum value. We would need to take derivatives. We would need to see where the function's going from positive to negative, and then that would give us our relative minimums and our relative maximums. That's a lot of work. We would also run into a problem after that, right? So we could maybe find out where our limits of integration are. But if I look at these areas on the edge, right? So purple to purple, it seems fine, right? We have the orange curve being on top. We have the blue curve being on the bottom. The problem would be when we go to these outer regions, right? What is really going on here, right? For that left green region, or maybe I'll just do that in pink so we can just speak about it better. What's the top versus what's the bottom function? It's actually just the area between the orange curve and the x-axis on both sides. So our integral, we'd have to have some separate integral for that area, right? Same thing for the lime green. Now we're really only worried about the area between the two pieces of the blue curve. So this would get pretty complicated. We'd have multiple different integrals, etc. So it just doesn't really make sense to go about this finding limits of integration in terms of x. Now, if I think about limits of integration in terms of y, and hopefully you've thought about that, but it actually becomes a whole lot easier. I would figure out the intersection points, and I'm not doing well at drawing lines in the right spots today. There we go, that's pretty good. So we'd have that intersection point, and I would have this one, right? And those would be two y values. We can go ahead and find them, right? But this line would be y equals something, and this line would be y equals something. And those would be our upper and lower bounds of integration. And then notice that we do have a top versus a bottom function here. This would be our top function, right? The blue. Again, because that has the higher x values over the interval. And this orange would be our bottom. If they weren't graphed, then you could go ahead and just test them by substituting in a point. So quite simple when we set it up in terms of y, right? Didn't really make sense to do in terms of x, but y looks a lot easier. Okay, now that we know we're going to set it up in terms of y, we need to figure out what our limits of integration are, and then we need to write out top minus bottom in terms of functions. So figuring out limits of integration, we could sort of tell. There's only two options, -2 to 3 or 1 to 11. Well, one of those pink lines falls above. One of them falls below the x-axis. So we know that our limits of integration are going to be -2 to 3. You could also set the functions equal to each other. Right? We could say negative y squared plus 3y plus 11 is equal to y squared plus y minus 1. Add y squared to both sides. Well, essentially, I'm just going to move everything over, right? So I'm going to add y squared. I'm going to subtract 3x, and I'm going to subtract 11 from both sides. That gives me 0 is equal to 2y squared minus 2y minus 12. Factor out the 2 and divide both sides by 2, so I get 0 is equal to y squared minus y minus 6. Factor y minus 3 times the quantity y plus 2. Voila, there's your solutions, y equals 3, y equals -2. Notice, though, on an AP exam, understanding that they have to be -2 and 3 because one side of one of those pink lines is above, one is below the x-axis, right, could save you a lot of time, right? Then you would not have to go through all of this work. But you could if you were unsure. Okay, going to get rid of that. We already know what our limits of integration are. I also know that well, let's just set this up actually. So we're going from -2 to 3, top minus bottom. Top function is the blue, so I get -y squared plus 3y plus 11 minus the bottom. So minus the quantity y squared plus y minus 1. Put those in brackets. We're integrating with respect to y. And then we just need to simplify, right? We just need to make sure or figure out which answer is correct. If I do -y squared minus y squared, that's going to give me -2y squared. We can probably just stop right there and know that it's going to be a, but let's keep going. 3y minus y gives me positive 2y. 11 minus -1 gives me positive 12. There we go. That does indeed match choice A. Do not have to evaluate this integral here. Okay, I think that's going to do it for this video. We've gone long enough. Big concept here, right, is that we can find the area between two curves by integrating with respect to y, setting up our interval in terms of y values rather than x values, and making sure our function is in terms of y rather than x's. Sometimes setting our integral up that way is going to make it much easier to evaluate. So again, as we go through these practice problems, you really want to think about why is it easier to integrate with respect to y, or why is it easier to set up in terms of y rather than x's. Because on the AP exam, you may have to make that decision, right? In this lesson, we're practicing setting everything up in terms of y. But on the AP exam, you're going to have to determine, okay, which might be quicker? Is it quicker to integrate with respect to x? Is it quicker to integrate with respect to y? And not every time will you just be able to look at the functions and make a decision based off of that, right? Like I said, a lot of times you will. If they're given to you in terms of y, a lot of times you're going to set everything up in terms of y. But I have seen questions where they're given to you in terms of x, and you're going to have to rewrite them in terms of y, because it just turns out it's much easier to do it that way, or vice versa. So just be always thinking, why is it easier this way? Why is it easier that way when we're working through these questions? All right, as always, enjoy the rest of your day, and we will look forward to seeing you next time.